In this chapter, we're going to talk about nuclear chemistry. And nuclear chemistry is pretty different from the other aspects of chemistry we've been talking about. Reviewing a little bit about how we talk about atoms in general, remember that we have an atomic number, which we abbreviate as Z, and that tells us the number of proteins. We have a mass number, A, which is the mass of the atom, so it's the number of protons plus the number of neutrons, because remember electrons are very small in proportion to those, and so they're negligible. So when we write the symbol for carbon, for example, we write the symbol C, and then we write the mass at the top left and the number at the bottom left. And that tells us that there are 6 protons, because that's how many there are in carbon. If it had a different number, it would no longer be carbon. And we get the number of neutrons by subtracting 12 from 6, and we get 6 neutrons. This happens to be the same this time, but it's not always going to be the same number of neutrons and protons. So an isotope is an atom of the same element, that is, they have the same number of protons, but they have a different number of neutrons, and so that is perfectly okay. That occurs in nature all the time. So just like we could have some things with different numbers of electrons, we can have different number of neutrons. But remember, the protons stay the same. If they change, then we no longer have the original atom or element. And so in this example, this is carbon because it has 6 protons, which means it's number 6 on the periodic table. And I can have 3 isotopes of carbon that vary only in the number of neutrons. The carbon that has 6 neutrons is carbon 12, because 12 minus 6 is 6. That's how many neutrons I have. Carbon 13, it's got 7 neutrons. Okay, so 13 minus 6 is 7 neutrons, so that's carbon 13. And then carbon 14 has 8 neutrons. And so they're all carbon, but they're different isotopes of carbon because they vary in the number of neutrons. A radioactive isotope, or also called a radioisotope, emits energy, and it does that because it's unstable. Things in nature that have too much energy, okay, too much energy equals unstable. And so what has to happen is it has to release energy in order to get to a more stable place. And so radioactivity is the nuclear radiation that's being emitted by a radioactive isotope. And of the known isotopes of all the elements, 264 are stable, 300 occur naturally but are unstable, that is, they're going to go through this radioactive decay. An even larger number of radioactive isotopes, called artificial isotopes, have been produced in the laboratory, and those are those that you see on that very bottom layer there, those transition metals that are all radioactive. They are very heavy, very high masses, and it's funny because, you know, they don't stay around for very long, and so it's one of those things where, you know, somebody made it in the lab and that's how they got their PhD when they wrote their paper about it. So you know, they're artificial, they don't really have any use, but you can do it. You can make them. Types of radiation. This is important. Okay, so you have alpha particles, beta particles, positrons, which are sort of the opposite of a beta particle, and gamma radiation. And gamma radiation, notice, is not a particle, it's just some energy. So an alpha particle is a high energy particle. It's got 2 protons and 2 neutrons, so it has a mass of 4, and it has a +2 charge. Okay, a +2 charge, and we designate that as the alpha, or you can also write it as 4/2 helium, because a mass of 4 with 2 protons is the definition of a helium atom. And so you can absolutely write it like that, especially if you were going to have to balance an equation. A beta particle is also a very high energy particle. It has a -1 charge because a beta particle is basically an electron. It has no mass, really, okay? It has no mass or very little mass, and it has a -1 charge, just like an electron. And a beta particle is formed when a neutron is converted to a proton and an electron. So you kind of split it apart and it becomes a proton and an electron. And that electron that's produced is your beta particle. A positron is like the opposite of a beta particle. All right, their charges are opposite, but their masses are the same. So they basically have no mass. A positron has a plus charge, and so we sometimes call it a positive electron. And so we do beta plus for it, and we write it as an electron except with the positive charge. A positron is formed when a proton is converted to a neutron and a positron. And notice that you have 1 on the top here in the masses, and you have 1 plus 0 is 1, and you have a 1 on the bottom, and you have a 0 and a -1, okay? And that's going to give you a 1 on the bottom as well, okay? Gamma rays. Gamma rays are high energy radiation. Oh, let me go back for 1 second. Oh, that should be a +1. When I said that out loud and then I looked at it again, that's a positron, so that should have a +1. That's why it's a 1. All right, almost missed that. Okay, gamma rays. Gamma rays are just high energy radiation, and they're released from your nucleus, and they're energy. There is no mass, there is no charge or anything, and so we designate as a gamma ray. So in summary, for your types of radiation, you have alpha particles, which are alpha or a helium atom with a +2 charge and a mass of 4. Beta particle is beta or 0 over -1, -1 charge, no mass. Positron, opposite of a beta, so we call it a beta plus, and it's written like an electron except with a plus charge, and it's a +1 and a 0. And then finally the gamma ray, which is gamma, which has no charge and no mass.